Hi, everyone. I'm Lou. So first of all, I want to say this is like supposed to be my meeting, but Anakin did do like all of the pictures, which is most of the slides. So Anakin helped a lot and probably did more than me. So thank you, Anakin. But today we're going to be talking about an algorithm from Knuth. That's very interesting. He called it algorithm X because he's really known for his descriptive algorithm names. And we're going to be kind of building on the exact cover stuff that we talked about last week.
The left click is go forward.
Whoops.
Yeah.
Yeah.
Oh no. Oh wait, hold on. It's because. Okay, that should work now.
Okay, wait. Yeah, so first when we yeah, so this is also an interesting algorithm because the weird part is really this like data structure that we construct to do the whole thing. Yeah, so if you weren't here last week, or if you need a refresher, so an exact cover problem is we need to select subsets of a certain, so we have a set of sets of items and we need to select, yes, the word subset appears too many times. So we have a list, we have lists of items and we need to select a subset of those lists that cover all of the lists and or all of the possible items. So we want to make sure that the union of the subsets is all of the items, but we don't want each item to appear more than once in a subset that we choose. So it's NP complete, which means that we are not going to get a particularly optimal solution for it, but there are still some cool things we can do to optimize, especially like memory usage and stuff, even if our runtime is always going to be pretty bad in the worst case. Yeah, so this is the example that we're going to be walking through today. So the goal is we want to select the rows so that each column in the selection has one. So not more than one, not less than one, exactly one. So in this case, we're going to be abstracting it. Instead of representing it as a matrix, we're going to represent it as, a list. And so you see here, like the first column is A, B, C, D, and then, so if there's a 1 in the first column, it turns into an A and B in the lists and options lists and so on. So we have this list of, we have these options, which are just lists of items, and then we are going to pick 1, 2, and 3 out of there, because then that will cover A, B, C, D, and E exactly once. And we're going, visually, this is not the most interesting example, but when you see the pictures, you will understand why we did not do a large bar.
Oh, wait, hold on.
What did I do? I think
your mouse moved. Okay, you're good.
Sorry, okay. So we talked about how to solve this recursively last week. So this is sort of just, so we have our items, we have our options, we have our existing cover, and we have I, which is the item we're trying to cover. So if cover is a cover, then we're done. If we can't cover I, then we're not done. And we can't finish, but we can't solve it, so we need to terminate unsuccessfully and go back. And then so recursively, we'll just say that we'll select an option that contains I, and we will remove is it removing the extra?
Moving the list.
Yeah, so we remove I from the options list, and if J is, so we'll go through all of the options or all of the items in that options list, and then cover all of the items corresponding with that item. The word item doesn't sound zero anymore. But yeah, so it's basically recursively we pick an option to try and cover the we pick an option to try and cover I, and if it doesn't work, then you try the next one and so on. And one thing you'll notice about this recursive algorithm is that it takes a lot of memory. So like options, items, cover I, all of those are being passed into a new function, so we're continually new stack calls. Anyone here know about the stack 233? Yeah. So recursive functions are always going to be more computationally expensive in that way. But we can actually do this in a way that will not require copying any new memory. So that's pretty cool. Yeah, so now we're going to talk about this data structure that Knuth has to represent this problem. It's kind of like a linked list. I hope everybody is familiar with linked lists? Yeah, so it's a linked list, but it has like imagine if a linked list had like instead of being like doubly linked, it was like octuply linked. Doesn't that sound fun? Anyway, so we started out with just a normal linked list. And so each of the items in the list represents each of the nodes in the list represents one of the items that we're trying to cover, so A, B, C, D, E. And later we're going to add on to this list, so like downwards. So this is like so at the top is this horizontal linked list. And also note that it's circular. Because why not? And then each of these items is then also going to have another linked list like coming down from it, and that's going to represent all of the options that we can use to cover that item. So it's easy to see with a picture. So if we use, so here's what happens. So here we've numbered all of these nodes like 0 through 21. The nodes on the edges like 6, 9, 11, 14, those are just sort of like spacer nodes, you call them. So those are just kind of to let us know that we're at the end of the line. And those will like store some information. We don't need to get into the low level details, but those are not actually representing options. So, but you'll see like that first line has 7 represents A, and 8 represents C. So you can see, yeah. So if you see these lines that connect them, underneath A, there's you see our first option 1 was something that could cover A, and so is our last option 5. And so 18 is like one from the ACD option, and it's it does look very messy. It is pretty messy. Does anyone have any questions about what any of these are? Oh, yes. What's a torus?
Yes, topologically, if you want to think about it, it's a torus, but that really has no bearing on how we.
Yeah, it's right.
I'm sure you could abstract it more, but you don't gain anything from it. And arguably, I think it's a lot easier to actually just think about this as this lattice of linked lists. You have nodes and you can move around.
Yeah, and I do also want to note that this is also a circular linked list. So the like 18 connects back up to A. So it's circular in both directions.
And then a very quick note. If it's hard to read, especially for those in the back, the slides are uploaded. So it may be easier to follow along with that. But otherwise, yeah.
Yes.
Yeah, sorry, I'm just wondering, like, so if I'm traversing this, like the link that starts at 1 vertically, how do I know that like 18 are we just drawing it this way for convenience of the lattice? Or are there like actually empty nodes in the middle? So
Yeah, so that's sort of what the spacer nodes are supposed to do. Like visually, they don't make much sense, but if you actually start implementing it, like you know that everything in between 17 and 21 is all one item, because 17 and 21 are spacer nodes, or sorry, all one option.
Okay.
So yeah, the spacer nodes will like group the options separately.
Gotcha.
Yeah, and so another thing to note that like you see the 7 and the 8, like they're not actually explicitly connected by a link. So the way that we traverse it in that direction is we just add. So 7 plus 1 is 8 if we want to get to the node, like sort of to the, which direction is this?
Right.
Yeah, so we want to get to the node to the right of 7, and we just add 1. And then if we want to get to the node to the right of 8, we add 1, then we get to 9, we know that that's a spacer node. So the spacer node will store some extra information that can get us back to 7. Yeah, so any other questions about this beautiful data structure? No, okay. So now we're going to talk about the actual algorithm. And so this probably won't make that much sense without the pictures, but we are going to get to the pictures, so don't worry about it. So we have a few helper functions here. One, we have hide p, and so p is a node P is a node that is in one of like the options. So if you have oh, now I can't see the picture, so I don't remember. But so you basically you take this node P and every other item that is in that. So every node that is like connected horizontally to P gets removed from that linked list. So it doesn't get removed because it's still sort of there. It's just that we rearrange the links so that you can't reach it anymore. And this basically makes it, well, so that basically makes it so that that option can't be chosen anymore. So yeah, so if you look at this, this is where we are hiding, I think. Yeah, so here we were trying to hide 7. So 7 doesn't actually really get affected by this, but if you look at 8, that is because 8 is horizontal with 7, we need to remove that from the linked list at C. So we do that by changing the C's downward pointer to go to 15 and changing 15's upward pointer to go to C. So they just sort of bypass 8. So 8 still has links to C and 15. 8 is just not accessible from C or 15. And so then there's also cover I, and so that's when we take an item I. So the items are A, B, C, D, E, the stuff at the top of the list. So and then sorry, there's that. So then it just hides all of the options that could cover this item. So this is, you know, again, this is an exact cover, so we can't choose an option that would cover something more than once. So we need to remove that. Once we have covered an item, we need to just get rid of all of the other options. So this is I believe this is the case where we're covering A using 7. And so this is just sort of where the hide actually gets used. So because we're covering A with 7, that means we're also covering C. And so okay, yeah, so we're also covering C, which means we're going to need to remove 8 and also we need to remove the list of 8, and then we also need to remove the 15. Or I may be mixing this up, but it will make sense. Oh my god, I'm so sorry. I don't know how to put through slides. So the actual algorithm, now that we've finally gotten there, is setting up. First of all, the first step is setting up this whole mess, and we're going to initialize a level variable L to 0 so that we can keep track of the level of our recursion. And so then we sort of enter this loop, and if all of our items have been covered, then we report success. We visit the answer, we can go over that a bit at the end, and then we're going to go to line 13 where the will 0 terminate, so then our program will end. So otherwise, then we select an item that hasn't yet been covered, we call it I. We're going to cover it, and then we are going to assign XL. So remember, L is an actual number, so there's going to be like an X0 and X1. We call it XL, and it could be, we don't know what L is at this exact moment. And so we're going to pick the object down, or the first node down from I. And first of all, so if XL equals I, then that means that the linked list is now empty, and so there's nothing we can really. We can't select any options here, so we need to backtrack, and that's going to be. Here is we're going to have to uncover I and step back through the recursion. Otherwise, so we need to select the option that corresponds to this node and cover every item in O. So we're basically, we're picking an option and we're covering all of the items that it covers. And so then we go back to line 2 and we pick a new item covered. So if we get to line 11, then this means we have to undo some stuff. We have to uncover the items that we covered that would correspond to XL, and we need to pick a new XL. So, yeah, I think this may be missing an XL, an XL reassignment, because you need to set XL to be XL down. Am I just missing that? No, just.
I don't think so.
You do need to reassign XL. I do. Anyway. Sorry, that is.
This algorithm makes a lot more sense pictorially, so I think.
Yeah, honestly, this algorithm doesn't make much sense either way, but it's better pictorially. Yeah, so again, this doesn't make much sense, but hopefully. Yeah, so I think I might have forgotten to mention that we just have uncover and unhide methods that just undo the things that cover and hide do. So that's not too difficult, because cover and hide just move pointers around, so we're not actually deleting them, so we just reverse that pointer. So, yeah, okay, now let's go through the actual algorithm. And so we've initialized the status structure, which we talked about before. And so then we need to initialize our level, so L equals 0, and then we also are initializing just a bunch of XLs. This is more for like a visual kind of thing, because we know that there can only be up to 5 levels, because there are only 5 options. And we're just going to show you what those end up being assigned to as we go through. So first we're going to select an I. In this case, we're just going to select A, because it's the first one on the list, and we are going to try to cover A. So the first part of covering A is we need to hide 7. So you'll notice we have like P and Q moving around as they happen, so those correspond with the pseudo variables. And so we're hiding 7. That means that we need to disconnect 8 so that can be chosen. And yeah, so there's only one other item in this option, so we just need to take care of that one. But then the next part of covering A is we also need to do the same thing with 18. So 18 has 2 horizontal neighbors. There are two other items in its option, 19 and 20. Those correspond to C and D. So we will need to hide both of those. So if you see here, we're sort of bypassing 19. So now the only item in the C list is 15. 8 and 19 are both sort of fake excluded. Then we need to do the same thing with 20. And we get to the spacer node, we go back around, we're done hiding. And then, so now that we've sort of covered A, we need to remove it from the linked list. And so this is, again, we're not, because it's a linked list, we don't actually need to delete anything. We just have these pointers between 0 and 2. Yeah, so does that all make sense? Are there any questions so far?
You're saying that like A doesn't actually go, but you don't have a pointer available. So like, how do you have it? So you got pointers out of it.
Yeah, so 0 doesn't have a pointer to A, or So, okay, so 0 doesn't have a pointer to 1, 2 also doesn't have a pointer to 1, but we can just store a pointer to 1 like separately.
Right, but what about for 8? Like 1 I get, but what about for 8? So are you like storing a separate array of pointers rather than like?
Yeah, so if you actually look at the book, there's sort of a table of what this looks like in computer memory. But yeah, basically, so we have like a list somewhere of all of these nodes somewhere else. It's just that in this data structure,
It's fine.
they're hidden, but we have somewhere else just like all of the nodes. And we also, because they're numbered, we can always just sort of loop through them and look through them and access them.
That's
So then this is like the spacer stuff, I think, right? Is that dotted line the spacer stuff?
I think so, yeah.
Okay. But yeah, so here now we're going to say that we've chosen that first that 7, we've chosen that as the option that we're going to use to cover A. So this means that we need to cover C because 7 and 8 both cover 7 and 8 are put together. So if we pick 7 and 8, we need to cover both A and C. We've already covered A. We need to go cover C. So covering C, there's only one element really left in C, that's 15. So we just need to hide 15, which means we need to disconnect 16 from that list over there. Does that make sense? And then yeah, then 17 is a spacer, so we don't have to do anything, and we get back to 15 and we're done. We also, so we come in C now, so we need to remove it from the linked list. So now you see 0 points to B, B points to D, D points to E, E points to the dash, the initial list thing. So, and we notice that we've also stored X0 to be 7. So that's how we're going to be keeping track of what options we've chosen to cover different items. Yeah, and so then this is just, yeah, so 9 again is a spacer, so we're still covering everything in this row, so we don't really need to cover anything related to 9, we can't skip that. And yeah, so now we're back at the beginning. We've gone through one level of recursion, and now it's time to do it again. So this time we're going to be trying to cover B. So we're going to go through this one a bit faster, but so basically we're going to be covering, there's only one option for B, so that makes it a bit easier, but we're going to be removing B from this list and using 12 to cover it. So we're storing XL, where XL is 1, we're storing that as 12. And then, because this also covers D, we are covering D, so we're going to be moving. Yeah, so then actually, I don't know if there's anything left to. Yeah, because 13 is the only item in the list for D2 now. So this leaves us with only this covered B and D. So now all we're left with is C. Did you have a question?
So I see our covered by there's some cover X0.
Is what covered by?
This X2 is supposed to be covered by 8. Considering the fact that we covered X0 inside.
Okay, so X0 and X1 and all of those, so those just correspond to the levels of the recursion. So they don't really correspond to like A, B, C, D, E. So they're not items, so it doesn't really make sense to cover them. So basically, like each of these is going to end up storing one of the options that we're using. So the option that we chose at level 0 was the option that includes node 7. And then at level 1, the option we chose included the option that we chose used node 12. So we're going to store 12. And then later we can use the 12 to also uncover the 13 and like the B and the D and all of that stuff.
Remember that each option contains multiple items. So that 7 not only really didn't only just cover the A, it covered the C because it contains both.
Yeah, so the options are being represented by one of the nodes in the option. And so it doesn't have to really be 7. If we had just picked C as our first. If we had picked C as like the first item we tried to cover, then X0 would end up being 8. It doesn't really matter. Yeah, and so you'll also notice that the linked list at the top looks kind of mangled, but it does. The 0 points to the 5 and the 5 points again, 0. And so now we have left to cover its B, so we're going to try and cover B. And going through this even quicker, so we're at level 2, so we set X2 to be 10 and remove E from the linked list. There's nothing else to cover here, so because 10 is the only item left for E, so now our linked list is empty and we can reconstruct the solution. Yeah, so this is our final state. Any questions about that?
Maybe I'm like misunderstanding this, but like if you took the like the bottom row, like you did to the top, like essentially if like you store your options in different order, would that affect the runtime or like would that affect how it reads the solution?
So the way that, okay, so I guess that would depend on how you were selecting the first option you were going to choose. In this case, yes, if we move that last row, if we like switch the first and the last row, then we would end up trying 18 before 7. So that the ordering is arbitrary, really. And so there are like some heuristics and stuff you can use to try and decide which order is best and like what order you should try to cover A, B, C, D, E in. But we decided not to get into that.
But in the 18th place, that would fail, and then once it goes through the failings, then they like not worry about that anymore. And then look at side.
Okay, so if it covered, if it tried to, yeah, so if it tried to cover A using 18, then that would also cover C and D. So then if it could try to cover B, that would be a problem. And if it tried to cover E, I think it could also just choose the 10. So I think you could just find a different cover by.
So, okay, it's gonna be hard to visualize because we didn't draw this possibility out.
Yeah.
So suppose that the first option you try is this one with the 18. Okay, you're gonna hide everything associated with option 7. You're gonna hide like the 19 and the 20, so you don't double select an option. And so we've selected 18. Cool. And so this option now also covers not only item A, but item C and item D. Right? And so we'll go and we'll try to we'll remove options hide options associated with C and D because they've already been covered. And then when we get to now we covered, so after it's all done, the only things that we can reach in our top linked list are B and E. And so here's where we run into the issue. Now we want to cover B. The only option that contains a B that corresponds to covering B also contains a 13, which would have been hidden by our process of covering item D earlier. And so then we would have to undo that. And that's where like the uncover and the unhide would come in, which is where you essentially reverse all the operations. So the point is, so basically the moral of the story is that the order doesn't really matter, right? We just put them in some order and we just walked through the algorithm that way.
So I mean, kind of just to recap, so it tells when it fails. By seeing the like if it looks at B and it's like, oh wait, I've hidden everything that can cover B, then it knows it's a fail state. So
Yeah.
Okay.
Yeah, and so I mean, even one possibility is maybe there aren't any options that cover B. because that is technically a state that you could be given. And so in that case, you would fail pretty quickly, because every time you tried to cover B, you wouldn't be able to find anything, because there would be nothing. But yeah. Yeah, and so now we've covered everything, so we're done. And now we get to talk about recovering the answer, which I've sort of talked about a bit. We just have our x0, our x1, our x2, and we're going to use that to recover the options that we ended up using to cover this. So each of the nodes in the data structure contains a field that points to, in this case, what is a link in this case?
Or no, that should say no, my bad.
Okay, so yeah, so each node has basically each node knows what option it belongs to. So you can just get that. So that's not too bad to recover. It's just the data structure design that's required to get to that point is a bit interesting. Does everyone see how to recover the options that you ended up using? I think we kind of talked about that earlier, so. Yeah, questions in general.
Well, is this like, this is an implementation question, so I'm not sure there's an implementation section.
We did not actually implement it. I don't hate myself that much.
I hate myself, so I'm working on it.
Yeah,
Yeah,
I saw that like basket weave and I was like, nope, the
yeah.
picture's bad enough.
So what's your
But
implement?
yeah, we can
It seems
implement
like, I mean, all I know is like, how many pointers would each link need to remember? Because it's like a struct, then you would have to like say how many, like, you need to like make a separate like, or would you need like an array of pointers that could be like an arbitrary amount?
So each of so there's the nodes that are kind of like internal down here are different than the nodes that are up there. And so in the actual text, there are some fields that we left out, some of them because they're not really necessary for this version, and some because just for clarity. For like 18 is supposed to have a pointer up and a pointer down, and also a pointer all the way up to A, so it should have like equals like a top pointer so that you can go all the way back up to A. And so that's how you know like what item it is. And so there's at least two because it needs an up and a down, and then 3 for the top. And then the ones up at the top have 2 outgoing pointers horizontally and 2 pointers vertically. So those are, I think, those ones do need 4 pointers each. And I mean the spacer nodes are all implemented completely differently because they're storing different things. So it's messy. The exact number depends. And like I said, so there's sort of an implicit link between like 18 and 19, but the link that in the way that we represent it is we just add them. So I guess that is kind of like an array. We probably, because we do have things numbered, we would probably have an array somewhere. I don't know if this is matching up with anything you've written yet, but
Yeah, so okay, so there are a couple other, if you're interested in implementing this, and Knuth does go into a lot more detail about how exactly to do this. And in fact, I think it's algorithm I in the text. It's one of the solutions to an exercise. It goes over exactly how, given just the list of items and options, how to set up this. And it goes into detail about for each node, you need to point to these things and the actual data structure design. So that's about. So full implementation details are actually in the text.
yeah, I left quite a bit out because I didn't want to be like, I didn't want the whole presentation to be like, then you reassign this pointer to point to that instead. So
yeah,
because it's I mean, when I was reading it, it didn't really actually help me understand what was going on. It was really the pictures, so.
I think the big takeaway for this is that, well, you said at the beginning that the recursive. So why does this have better space than the recursion?
So this doesn't actually copy anything. So when you call the recursive function, I guess there like are ways to sort of implement this recursively if you're like passing it in like by reference or whatever, if you're using C++. But if like you're just sort of naively using recursion, then you need to like copy all of the data every time you call a new function. So this is a way to work around that. Yeah, because you can't let your different like layers of recursion interact with each other. So if you are passing things by reference, it can get a bit interesting. So
Yeah. So the nice thing is we've gone from exponential space to basically linear time space, like linear space in the size of all the options we have. And so that greatly increases efficiency. And we've done it using linked lists, which is kind of interesting. So that's probably the big takeaway.
I really think, do you guys think that Professor Nowak would want to make this an FB? I hear he really likes linked lists. No? Okay. They do 4 linked list MPs in 128. I don't know if they do anymore. Incredible.
Regular branch, there's no regular branch list, it's a circular branch. And I think we're playing on one of those, it's going down the bottom,
Incredible.
cutting down the branch.
Wow.
It's just circular. Branch was more than circular, but I think that's circular.
Circular, I think, has more use cases than branch. Like this, look, it's a circular linked list. It's five circular linked lists.
How would you want to do this? Oh, actually, I don't want to like.
You have an area of pointers to all the elements, so walk down that area.
Yeah, pretty much. Yeah.
The book goes into all the details for this.
Yeah.
There's a lot of detail.
Yeah, and I mean, there are some clever things you can do, but you can also really naively store a lot of this information. Like you can just sort of like actually store somewhere like, okay, 7 points to this option over here. And then in that, we get that 8 is also part of that. So if you wanted to remove the like weird addition, the weird spacer bars and stuff, you could do that. Visually, I think that spacer bars make sense. But they are a bit weird to implement. But they are, again, necessary if you're just keeping track of things by adding. So.
Anyone have any other questions?
Has this inspired anyone to go implement a linked list? Has this convinced anyone that linked lists are a useful data structure? But yeah, so he calls like the way that he sort of manipulates the linked list, sort of like a move elements, a dancing linked list. We didn't get too much into that. But yeah, so he does have very detailed instructions on it, on the implementation details. And yeah, Anakin was gonna post that online if anyone does it. So
Yeah.
if you want
Anyone wants to implement it, or I might start implementing it in like a public copy if anyone wants to go through that. My high level plan is I want to kind of implement this in like a bunch of the optimizations.
Yeah, because there are a lot of optimizations to make. It's just.
So yeah.
Yeah. Yeah, and so you can, if you want to walk through this, like we did, it's a really good way to get to understand the algorithm. And especially we sort of brushed over the uncover and unhide, but they are really important parts of the backtracking. So if you really want to understand this algorithm, you can go look at those. I just didn't want to think too much about pointers.
Get a fill in.
So anything read all the pictures like 10 times.
Yeah. All right. Thank you all for coming. I hope you guys got something out of that. Just this idea of using linked lists to greatly improve space, and that the fact that it's even possible. I know linked lists aren't something that you really see in actual use. So it's kind of cool to see this. Yeah, thank you all for coming.